to a new steady state, we can find that new steady state as limit as t goes to infinity of y prime of t. Okay, the new steady state is, so we can use our 3 steps, find u prime bar, di prime bar, and then y prime bar, then partial fractions expansion, inverse, find y prime of t as we've been doing, and then just take the limit y prime of t goes to infinity.
How to use the amount of that change? You said the change twice 3, right?
Yeah, you have to specify what is the change in the input, yes.
How to embed that in y of t equation?
That's, so if you're, okay, if I tell you if u increased by 3, that means that u prime, which is u minus u naught, u increased from u naught to u naught plus 3, u prime is going to be 3. So u prime bar is going to be 3 over s. So you plug 3 over s for u prime bar, and we'll see. So if I tell you the input increased by 3, that means u prime bar is 3 over s. Clear, everyone? Thomas? So, one way you can get it is by taking time goes to infinity. But we can do it a lot faster and better using what Alden alluded to, which is the final value theorem. The final value theorem says that the limit as time goes to infinity of y prime of t is of any function is the limit as s goes to 0 of s times y prime bar. In general, actually let me write it first. Okay, let's leave it like that. Let me write here limit is t goes to infinity of f of t, if it exists. There's a big if here. I mentioned previously, and I gave you the condition under which it exists. That's the final value, and applies to any transfer function. Well, we know that y prime bar is gu of s plus sum of g di of s di prime. So that is equal to limit as s goes to 0 of s times gu of s u prime bar plus sum of g di of s di prime bar. Right? What I did is I put for y prime bar, gu u prime bar plus sum of g di prime bar. Okay? Ready? Mika.
I'm having a hard time figuring out what does the eigenvalue thing mean.
Just giving you connection to what some of you were exposed in COD.
Okay, but it's only the eigenvalue today?
Yeah. Yeah, I show you here that the denominator of the transfer functions is the same as the eigenvalues. So the poles of the transfer function are the eigenvalues.
Oh, so the poles of the whole equation are the eigenvalues?
The poles of the transfer function are the eigenvalues. Yeah. That was the connection. All right. So go back here. Let's see what we can do about this limit. You can break it into sum. So I can rewrite this as limit as s goes to 0, and I'll write this as I'll write it as different parts. So let me explain what I did here. I limit. Let's start. So all I have done here is I have rewritten this equation. I have broken this into the two pieces, and limit of sum is the same as sum of limit. So I put the limit inside the sum of this, and I have here s g u u prime bar. For some reason, I decided to move the s and write it between the gu and the u prime bar. Okay? Just algebraic. All I did is get this limit of s times y prime bar. Y prime bar is gu prime bar, and for its disturbance, sum of g di prime bar. And then what I'm doing is the limit of the sum of the terms, I will write as the sum of the limit of the terms. If the limits exist, limit of sum is sum of limits. And so hopefully it's clear, just algebra. And you should know that if I have a limit of a product, a limit of AB, if limit, whatever limit we have, of A exists, and the limit of B exists, then limit of A times B is limit A times limit B. Okay? If both limits exist, limit of a product is the product. So I'm going to rewrite each of those limits as a product of two limits, because I'll tell you they will exist. So I will rewrite that as limit s goes to 0 of g u of s times limit as s goes to 0 of s times u prime bar plus the sum for every disturbance. I'll do the same thing of the limit as s goes to 0 of g di of s times the limit as s goes to 0 of s times di prime bar. Okay, all I have done is have those limits, and I have regrouped them. I'm saying that these limits exist. If they exist, I can. Okay. What's the limit as s goes to 0 of s u prime bar?
0. U prime.
Adam.
For this u prime, whatever the increases, right? S times 7 over s.
Okay, Adam is thinking correctly. So I had some zeros, and Adam is arguing not 0. Adam, maybe you can be a little bit more specific.
U prime b.
What time?
At 3.
Uh-huh. Look at the final value theorem. We said limit as time goes to infinity of f of t is this limit. That's the left-hand side of it that we looked at. Now look at it from the right-hand side. The limit as s goes to 0 of s times the Laplace transfer of something is not 0. It's the limit as time goes to infinity of that value. It's a steady state value of something. So this limit is not 0, it's u prime infinity. It's the change that Adam mentioned. You reasoned out that value, that's why it is that value. Okay? So that's u prime infinity. So we get, so let me continue. Well, I was writing stability, so let's continue writing stability. So if stable, if GU and all GDI are stable, none of them has any pole positively apart, okay? And if all inputs reach constant values, as t goes to infinity, if the level of as time goes to infinity, then y prime reaches a new steady state. And that new steady state, which is limit as t goes to infinity of y prime of t, is, what do we get from here? What's the limit as s goes to 0 of GU of s? It's put for s to 0. That's what it is. So that's going to be GU of 0. So this limit here is GU of 0. And this limit here, as Adam reasoned out, is u prime infinity. All right, like that is the new steady state value of u prime, is the change in u. So we will get GU of 0 times u prime infinity, and for its disturbance, similarly, this is the new constant value of u prime, which is the constant value of u minus nominal steady state. This is the new constant value of the disturbance minus steady state. So I can immediately find the new steady state value. So let's look at the example I put up there. What are the poles for this one? Continue, Nika. Okay. Do all of them have negative real part? All of them have negative real part. So we satisfy the condition for stability. And what did I tell you? U increases by 7, which means u prime is 7. Right? Originally at the nominal steady state, the change is 7. So u prime infinity is 7. So the new steady state limit as t goes to infinity of y prime of t is going to be GU of 0 times 7. So that's going to be minus 2.1. GU of 0 means wherever you have s, you put 0. So divided by 5 times 2 plus 20i, 2 minus 20i, times e to the 0 times 7. So what do I have here? This is 4 plus 400. So this is 404. So that's 2,000, right? Roughly 2,000. So minus 2 over 2,000 is minus 1,000 times 7. It's approximately minus 0.007. That's what I figured out. I'll end up at minus 0.007.
Why do you neglect the S plus 10?
What is the S plus?
10.
Well, that's a different example.
Oh, this is a new.
This is the first example I put. This is the second example. For this one, okay, let's say for this one, if, let's say, Z decreased by 4, what would be the new steady state? If Z decreased by 4, I would have y prime at infinity. The new steady state value would be gc of 0 times 4. And gc of 0, put in 0 wherever I have, so that would be minus 1.5 times 2 divided by 10 times 5 times 1.1 squared plus 12 squared times 4. So what did I get myself into here? Okay. 144, 145 times 10, 1,450 minus 12 over 1,450. So that's about minus 100. Very roughly. So the new steady state value, minus 100. Minus 1.
For that one, we said C raised by 4 with the.
Oh, decreased. Thank you. Minus 4. Oh, very good, Alba. Yes. Thank you. Mika.
What happened to the second term in the equation?
Oh,
That was the
this time? I didn't have a change in the disturbance. Okay, let's do a very quick third example. All right. Y prime bar equals, let's say, 3 over s plus 4 e to the minus 2s u prime bar minus plus minus 5 over s plus 2 e to the minus 3s d1 prime bar. Okay, here I'm making a mini problem. If at time 0 d1 increases by 6, how much should we change to ensure that the system ultimately returns to the original steady state? Here's a mini problem. So I'm saying